Okay, I want to talk to you a little bit here about pH and how to calculate pH. Now, obviously, this is the pH formula that is given in your data sheet to calculate pH, and it says pH equals minus log the hydronium ion concentration. So if you get a solution of, for instance, hydrochloric acid, and they say this is the concentration of hydrochloric acid, you just substitute into this equation the concentration of the hydronium ions and you will come out with a pH. However, most of the time they're more likely to give you the pH in the question and ask you to calculate the hydronium ion concentration. So all that you have to do is substitute in. You have to do the inverse operation of logging, which is raising to a power. So you literally take whatever the value is in the question, and then you get your calculator and you say 10 to the power of negative pH, whatever the value was given in the question. Let me see if I can bring my calculator up to show you. You can do it shorthand. See here on the calculator, you can see the log button on the calculator. So if you want to calculate pH, you use the log button by itself. But if you need hydronium ion concentration, you must go shift log and you will get 10 to the power of, and then you just type in here like whatever the value is, -4. So say you had something with a pH of -4, you go equals, and you will get your answer when you press the SD button, and that will be your concentration in moles per cubic decimeters. So it is 10 to the power of negative pH is going to give you the hydronium ion concentration. So that's all pretty straightforward if you are just wanting to calculate pH and you only have hydronium ions and you have an acid. If you have a base, you're going to have to take a further step. So when you find the pH of a base, you can normally have the concentration of the hydroxide ions. Remember, we have H3O plus, the hydronium ions, and the OH minus, the hydroxide ions. Okay, so our pH formula says minus log H3O plus, but if they gave you a base, then you will know your hydroxide ions. So your job is then to change it to hydronium ions. So you use the pH formula along with the results of this reaction. Now this reaction is the autoionization of water. The moment you put water in a container, there is an equilibrium system going along. It's a very weak equilibrium, but the moment you have water, liquid, with another water molecule, liquid, it will split into these hydronium ions and hydroxide ions. And so, you know, for any system at the steady pressure, you can calculate an equilibrium constant at a steady pressure and temperature, and for this one it's usually at 25 degrees that we do these calculations. So what happens is you will get an equilibrium constant Kc for this reaction, but because it's water we call it Kw for water. And so to make any equilibrium constant, the only thing we can look at is things in aqueous solution and gases. We may not use liquids and we may not use solids. So to form the Kc expression, which we're calling Kw, you will have the concentration of hydronium ions multiplied by the concentration of hydroxide ions. And provided you keep the temperature constant, you will get this value 1 times 10 to the -4. And so if you then use this equation, 1 times 10 to the -14 equals the H3O plus multiplied by the OH minus, you can substitute any value in there and get your final answer. So I'm going to show you how to do that now. So let's have a look though first. If you want to calculate the pH of a strong acid and you want to know the steps, you can freeze or pause your screen over here, and if you pause your screen over here you can write down these steps. The most important thing when we find pH is to realize that an acid and the hydronium ions may not have the same concentration. So the first step is to write down the ionization reaction. So for instance, for hydrochloric acid it's easy. Hydrochloric acid goes to a hydronium ion and a chloride ion. Okay, so for every 1 molecule of hydrochloric acid, hydrogen chloride, we will get 1 mole of hydronium ions. However, if you've got sulfuric acid and you then look at what happens to sulfuric acid, you end up with 2 protons and 1 sulfate ion. So for 1 mole of sulfuric acid, you get 2 moles of hydronium ions, and that is why this mole ratio step is important. So once you've got the mole ratio, if you have the concentration of the acid, you can then find the concentration of the hydronium ions using the ionization reaction, and it's mostly only a problem with polyprotic acids, okay, that you have to be careful with this. Once you've got the hydronium ion concentration, you just plug it into the formula and you will get your answer. So that's fairly straightforward. So now I'm going to show you what will happen if you want to calculate the pH of a strong base. You have to write down the dissociation reaction again. Okay, for instance, sodium hydroxide will split up into the sodium ion and the hydroxide ion. And so there's a ratio of 1 mole of sodium hydroxide to 1 mole of hydroxide ions. But if you have calcium hydroxide, this will split up into 1 calcium ion, Ca2+, and 2 hydroxide ions. So the concentration of the base and the concentration of the hydroxide ions is not the same. This is 1 mole, this is 2 moles, and that's why we do this step. So that is write down the dissociation reaction, determine the mole ratio, determine the hydroxide ion concentration based on the mole ratio, and now what you have to do is you have to use Kw. You use the Kw reaction and you know the OH minus, so you substitute the OH minus into there, and that will give you the H3O plus concentration, which you can then put into your pH formula. But don't worry, I will show you an example now. But if you wanted to write down the instructions, there are the instructions. Okay, so let's have a look at some past paper questions. Here is this first question over here. This one over here is the November 2020. This is the paper 2 that was not going to be marked. So it says to you, ethanoic acid is an ingredient of household vinegar. Is ethanoic acid a weak acid or a strong acid? Well, it is a weak acid because it ionizes incompletely, giving you a low concentration of hydronium ions. Now it says to you it has a pH of 3,85 at 25 degrees. Calculate the concentration of hydronium ions in the solution. So you say pH equals minus log concentration of hydronium ions. Okay. And then we know the pH is 3,85, so substitute in for the pH minus log hydronium ion concentration. So now by algebra we must do an inverse operation to calculate the hydronium ion concentration, and the inverse operation of logging is 10 to the power of something, so it is 10 to the power of negative 3,85. So here the hydronium ion concentration, if you put it in your calculator, it's going to be 1,41 times 10 to the negative 4 moles per cubic decimeter, because that's the unit. Let me see if I can get the calculator up to show you here. Okay, we go shift log, so I've got 10 to the power of, and then I go negative 3.85 equals, and there is my answer, and round it to 2 decimal places, 1,41 times 10 to the negative 4. Obviously though, if you're using this number in a calculation, try and keep the number in your calculator, don't round it off too early. But for the final answer for the concentration here, you can just write 1,41 times 10 to the negative 4 moles per cubic decimeters. Okay, now let's look at this June 2017 question. It says to you, ethanoic acid is an acid that ionizes incompletely in water according to the following equation. So it says, write down the term used for the underlined phrase. This is a weak acid. Okay. Now it says an ethanoic acid solution has a pH of 4 at 25 degrees. Calculate the concentration of the hydronium ions in the solution. So we do the same thing again, pH equals minus log H3O plus. So 4 equals minus log H3O plus. Therefore, the concentration of the hydronium ions is going to be 10 to the power of negative 4. So the concentration of the hydronium ions will be 1 times 10 to the negative 4 moles per cubic decimeter. Okay, so those are two fairly straightforward calculations, taking the pH back to a concentration. Okay, let's have a look over here. Now here is one from February-March 2016. It says define an acid in terms of the Lowry-Bronsted theory. Well, it's a proton donor. So it says here, carbonated water is an aqueous solution of carbonic acid. H2CO3 ionizes in 2 steps when it dissolves. Write down the formula of the conjugate base. Well, this is a 2-step ionization, but the final product, when it's lost most of its protons, will be the carbonate ion CO3 2-. Now, I'm not going to write the balanced equation for the first step because I don't have space, and we're mostly interested in this. It says to you, the pH of a carbonic acid solution at 25 degrees is 3,4. Calculate the hydroxide ion concentration. So it wants you the OH-. It does not want the hydronium, it wants the hydroxide ion concentration. So from the pH and the pH formula, okay, we can calculate very easily what the hydronium ion concentration is. So 3,4 equals minus log H3O plus. So the concentration of the hydronium ions is going to be 10 to the power of negative 3,4, which will end up being 3,981 times 10 to the negative 4. So you should keep that in your calculator. That's probably the first 3 of the 5 marks. Now it says to you calculate the hydroxide ion concentration, and this is where we use the dissociation of water and the Kw, because we know the H3O plus, okay, and it said to you here this is at 25 degrees, so we know that the equilibrium constant, 1 times 10 to the negative 14, which we'll read off the data sheet, is going to be equal to the hydronium ion concentration multiplied by the concentration of hydroxide ions. So therefore, by inverse operations on your calculator, you're going to say 1 times 10 to the negative 14 divided by 3,981 times 10 to the negative 4, and that will give you the hydroxide ion concentration. Okay, on your calculator this should be something like 2,51 times 10 to the negative 11. Just check on your calculator, do the sum on your calculator so you can figure it out, and my units will be moles per cubic decimeter. So that's the February-March 2016. Now let's have a look at November 2014. It says nitric acid is an important acid used in industry. It's a strong acid. Why is it a strong acid? It ionizes completely, giving you a high concentration of hydronium ions. Write down the name or the formula of the conjugate base. That'll be the nitrate ion, NO3-. And then it says calculate the pH of a 0,3 mole per cubic decimeter nitric acid solution. So this is the simplest way that you can do this. It says to you 0,3 moles per cubic decimeter nitric acid. So the first step is to write down the dissociation reaction, and from the dissociation reaction we will see that the mole ratio is 1 mole is to 1 mole. So it's fine to use the concentration of the acid as the concentration of the hydronium ions. So we'll just put in our calculator pH equals minus log 0,3. Press the buttons on your calculator and you will come out with a pH value of 13,30, and that one is quite simply done. And that leaves us with the last example I want to show you. This is from the KZN trial exam. This is KZN September 2020. Okay, it says learners were required to find the concentration and percentage of ethanoic acid in household vinegar. To do this, they used the following procedure: diluted a vinegar sample. This is not what we're interested in. Then it said titrated the vinegar sample with a solution of sodium hydroxide of concentration 0.2 moles per cubic decimeter. Calculate the pH of the sodium hydroxide solution. So we know pH equals minus log the hydronium ion concentration, but we have a base here, so we can't use this. We have to use the kW before we can use the pH formula, because we are going to want to calculate the hydronium ion concentration. So the first thing to do is to check the dissociation reaction. Sodium hydroxide dissociates into 1 sodium ion and 1 hydroxide ion, so this is 1 mole to 1 mole, so the mole ratio is 1 to 1. So we can use the concentration of the sodium hydroxide as the concentration of the hydronium ions. So the concentration of the hydroxide ions is going to be 0.2 moles per cubic decimeter. So we come now to the kW formula, which is the hydronium ion concentration multiplied by the hydroxide ion concentration. So we don't know this H3O plus. This is what we're trying to find in order to calculate pH. This is 0.2, and this is 1 times 10 to the negative 14. So if you put this in your calculator, you will end up with a concentration of hydronium ions being something like, where is this? I think I told you the wrong answer in the previous question. I've told you the wrong answer in the previous question here. Did you put this in your calculator? Where is this previous question? Sorry for jumping around like this. Let me just check here. Minus log 0.3. This is not 13. How did that come out of my brain? Put this in your calculator, people. Get your calculator and check me. This should be 0.52. Why did I have a basic pH for something that's an acid? Silly me, sorry. I checked the wrong number. Okay, so we fixed that November 2014 question. Let's go back to this KZN question, which I was busy with here. Sorry. So to calculate the concentration here, are you back with me again? Remember, we were looking at a base over here, and it was this pH that made me realize that I had answered the previous question wrong. So sorry for jumping around. So if you look here, if you put 1 times 10 to the negative 14 divided by 0.2 into your calculator, you should end up with something like, I should want to get out my calculator here, but I think it's 5 times 10 to the negative 14, and that will be your hydronium ion concentration. And only now can we use the pH formula, because by having used the ionization of water, we went from having a hydroxide ion concentration to a hydronium ion concentration. And so here we can put in here minus log 5 times 10 to the negative 14. And if we put that into our calculator, we will get 13.30, which is our final answer for the pH. And that makes sense. It's a pH higher than 7. It's a strong base. It's a pH close to 14. So we've done this correctly now.